Okay, welcome to this particular lecture. This is over section 2.4, which entails chemical reactions, activation energy, and then we'll compare endo and exothermic reactions. So what action? Well, anytime that you make or break a chemical bond, it's going to give off some form of energy, and usually that's in the form of light or heat. So you can see here fireworks, so that would be a chemical reaction. And that also takes place in your body, in your cells, and we'll look at that a little bit. Okay, so why do we need to have chemical reactions in our cells, in our bodies? Well, one reason is so it can make new molecules. You need to be able to maintain those cells. Energy. It can either be stored, used for work, or it can be immediately released. So here's an example. I need to define what CPE is. That's chemical potential energy. So let's say that you eat a hamburger or a sandwich or whatever, and within that piece of food, we'll just use a sandwich, there are compounds, proteins, carbohydrates, and fats. Well, that's going to be broken down into our building blocks of these macromolecules, and we covered that in our last lecture. So the protein would break down into amino acids and so forth. So, and then those building blocks would then be converted to ATP, which is an energy that the cells use. And then from there, the body would use it either as work or given off in the form of heat. Now, chemical reactions, you'll do this a lot in chemistry. On our exam, this will be an extra credit questions, so you can practice. I will have some practice problems and walk you through it if you've never done it before, or just a refresher course. So I'm just going to point out a few things here. First of all, in order to be balanced, you need to have the same number of atoms on each side of the equation or each side of the arrow. So on this side are my reactants on the back side of the arrow. Here's hydrogen, oxygen, and water, something very simple. And it's going to produce, or the products would be water. So in order to balance the equation, you need to have the same number of each element or atom on both sides of the equation. So on this side, I've got a total of 4 hydrogen. So I take my subscript and my coefficient and I multiply. So this coefficient will apply to every atom behind it, no matter if it's 1 or 20, it does not matter. And then unless it's separated by a plus sign, then it doesn't apply. So oxygen would only have 2, hydrogen on the product side would have 4, and then oxygen in this case would have 2. Now I underline the coefficients because that is the only number you can change or alter. You cannot mess with the subscripts. That's set. So I know I've seen it in the past, some people will actually draw little diagrams or use like a little tally mark. Whatever works for you, it does not matter. Soon you'll be able just to look at it and see. But in this case I've got CH4, so I have 1 carbon, 4 hydrogen. I'm going to combine that with a total of 4 oxygen. So I really like this diagram. It shows a visual, and it also breaks it down, and it tells you how many of each. So I've got 1 carbon, okay, and 2 oxygen. Now you notice the 2 does not apply to the carbon, only directly behind it. 4 hydrogen and 2 oxygen. Here's just another example. You can pause this and take a look at it if you want to, and you'll notice that, for example, on this side I do want to point out, on this side of the reactants I have 10 oxygen. Total on this side here is 6, so 3 times 2 is 6, plus 4, so that gives me a total of 10. So just be careful about that. Okay, our next thing we're going to talk about is equilibrium. And I know you've seen this every day in real life. For example, if you make Kool-Aid, okay, and we've had that example before, and you just pour the Kool-Aid packet in, and it's really concentrated, so that would be an example on this side, okay, and once I start stirring it, it disperses evenly out. So the key word here is state. So once it's reached its state where the reactants and products, there's no more change, I've mixed it thoroughly, everything is balanced, that is a state, it has reached equilibrium. So just kind of look for that key word. Okay, now we're going to move on to something activation energy, and I strongly encourage you to read this in the book and really study these diagrams. Okay, so the activation energy is the amount of energy, whatever that may be, in order to start a chemical reaction. Every chemical reaction needs some type of activation energy. So if I was to look at this particular graph, here are my reactants, and at the end are my products. So this green line, I'm going to add heat. That is my energy that I'm applying to whatever this reaction is. The red line is my activation energy. You notice that there's a delay. So I apply heat, and then the energy is going to start. You notice that there's increasing, and once it's kind of reached the plateau, maybe this is the boiling of water, then it's going to decrease and create my products for my chemical reaction. Okay, we'll come back to this in a second. But you'll see an endo and exothermic activation energy will work with that. So exothermic, exo means out or given off. So this would be, in this case, light. So the products would have a lower energy than the reactant. So it's giving off this particular energy. Endothermic is absorbing the heat. So the frying of the egg, the pan and the fire below it, that's the heat. The raw egg will absorb the energy, and that's what causes it to be cooked. So the products would have a higher energy because it's absorbing the heat. Okay, here's our activation energy again. I know they look almost the same, but you really need to look at it carefully. So here's my reaction as it progresses. Here's my energy applied on both cases. Okay, so my reactants, you notice where it starts right here. So this would be for exothermic, my light. And so the light is burning. And the activation energy, okay, is this much. Okay, so it's very minimal. And then it's going to drop off for the products. So that's why it says products have a lower energy than the reactants. So a lower energy than the reactants. On the egg side, for the endothermic, you notice the reactants start here at the bottom for potential energy, and it needs a lot of heat energy to cook that egg. Oops, sorry about that. So, and then my products are higher in energy because it's already been cooked, and that's the energy absorbed, which is the same. Energy absorbed, energy released. Okay, you can pause this right here. This is just another diagram. It's actually the right side for the exothermic is looking at the water, and on the left side for the endothermic, this would be my nitrogen oxide, and you might see that as a discharge from lightning, thunderstorms, and you can also see it in humans. But the endothermic needs a continual input of energy. Okay, so this would be my egg. So I need to have the fire on to keep the egg cooking. If you turn the heat off, it's going to stop cooking where you turn the heat off. For the exothermic, okay, it has a low activation energy. So once you have the candle lit, it'll keep burning until it extinguishes and has no more fuel. Okay? So do take some time to look over this, make sure you kind of understand the activation energy and how endo and exothermic differ. So that is a very short lecture. So do read in your online textbook, section 2.4. Take any notes I did not cover. If you need to add some more to the endo-exothermic activation energy section, do that. And so if you have any questions, come see me in class. So I'll see you later.